So, with that, we're going to talk a little bit more about this concept of limiting reactants. Okay. Now, up to this point, whenever we've done any of the stoichiometry problems, all of the problems have only said that, hey, look, if you start at this starting point and you have this amount, how much product will you get? Or what reactant do you need? And it always assumes that you have plenty of the other reactant. So if they give you one reactant, they say, it burns in excess oxygen or in plenty of oxygen or something along those lines. All of the problems that we are done so far are assumed to be what are known as stoichiometric mixtures. So let's say, for example, we have this chemical reaction where nitrogen, 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia gas. This is the same stuff that's in Windex, or same stuff that makes cat urine smell so pleasant. Yeah, right. But that's ammonia gas, okay? Now, before the reaction, we have a certain amount of nitrogen and a certain number of molecules of hydrogen. And it's assumed in these perfect problems that we've been doing that all of the nitrogen and all of the hydrogen will react, and you'll end up with nothing but ammonia after the reaction. Well, unfortunately, it doesn't, in the real world, it doesn't really work that way. You see, most of the time, you're going to end up with something left over. So in this case, you're going to have a certain amount of hydrogen, a certain amount of nitrogen. It looks like all the hydrogen gets used up, but if you notice, not all of the nitrogen, the larger ones here, get used up, and they are left over. This is known as a limiting reactant problem or reaction, okay, a mixture, where when you're all done, you still have at least one of the reactants. All right. So we know by doing, stoichiometry that in a reaction, reactants are used up in specific whole number ratios. All right. These are the coefficients in a balanced equation. That's the 1, the 3, and the 2. Now, since reactants come in different amounts and they're used up at different rates, in the real world, some are usually left over. All right. And the reactant that is left over is called the excess reactant. All right. It is an excess. There's too much of it, as it were. Limiting reactant, that's what we call the reactant that runs out first. Now, keep in mind, this particular reaction has only 2 reactants. One of them is going to get used up. That's the limiting reactant. One of them is going to be left over. That's the excess reactant. If you have more than 2 reactants, that's fine. One of them will be the limiting reactant. More than one can be the excess reactant. But every one of these problems is going to have one limiting reactant. Because when the reaction, basically when the limiting reactant runs out, the reaction stops. All right, it's kind of like something along the lines. Imagine that you are building bicycles, okay? And you work at this bicycle shop and you're making some really cool custom-made bikes. And you got lots of orders and so forth. And you come into work one day and you realize that you made a mistake in the ordering. And even though you have to make a whole bunch of bikes that day, you're down to like 15 tires and 9 seats, let's say, okay? You only have 15 tires and 9 seats. And the question would be, well, how many bicycles can you make with 15 tires and 9 seats, all right, before you have to stop? Well, if you think about it, the fact that you need 1 seat per bicycle means that if you're just looking at the seats and not worrying about anything else, you could make 9 more bicycles, right? But the fact that you only have 15 tires and each bicycle needs 2 tires That means that you can build only what? 7 bicycles. And as soon as you finish building that 7th bicycle, you're done for the day. All right. You have to wait until more, both tires, specifically tires, and also probably seats, come in from your supply. All right. Because as soon as you make that 7th bicycle, you've used up 14 of the 15 tires, and boom, you're done. The reaction stops. That's what happens here. So the reactants run out, and therefore the reaction stops. It therefore limits the amount of product produced. All right? The 15 tires limit how many bicycles you can make. You are limited to only 7 bicycles. Therefore, that's why we call it the limiting reactant. In the example I showed you with the jars just a second ago, the hydrogen gets used up first and the reaction stops, even though there's more nitrogen left over. So in that case, the hydrogen is the limiting reactant, while the nitrogen is the excess reactant. Now, that's the concept. Hopefully that's not too hard to grasp. The problems, those can be a little bit more challenging, as it were. You see, in a limiting reactant problem, what you are given here is that you're given the amount of at least 2 of the reactants. It's like me telling you how many tires you have and how many bicycle seats you have. Now, what you're going to have to figure out and basically do is these problems involve doing 2 stoichiometry grids. All right? You're going to use stoichiometry to convert the given amount of each reactant to an unknown amount of a product. All right, so yay, you're going to need 2 grids per problem, 1 for each starting point. But the trick is they both have to go to the same endpoint. All right, that way you can compare. And if the problem only asks you for if the problem asks you for a specific product, that's the one you should use. All right. If it just asks what's the limiting reactant, then you could choose any of the products. But most of the problems that you guys are going to encounter is going to be something like, all right, if you have 17 grams of hydrogen and 42 grams of nitrogen, how many grams of ammonia can you make? So you start off with the 17 grams of hydrogen, and you figure out how many grams of ammonia you can make. That's 1. And then you take the 42 grams of nitrogen as in a totally separate grid and go to the same endpoint, an unknown number of ammonia, unknown mass of ammonia. You do it twice and then you compare. All right. It's just like when we did how many bicycles can you make? Well, if I look at just the seats, I can make 9 bicycles. If I look at the tires, I can make 7 bicycles. Which one is the correct answer? The lesser of the 2. Okay? The lesser the amount of the product, all right, that's how much is actually produced. And then you go back, the reactant that produces that lesser amount, that's the limiting reactant. Whereas the other one is the excess reactant. All right? So, and if the question asks for the amount of product produced, you choose the lesser amount as your final answer. All right? So I'm going to show you guys a sample problem on how to do that right now. So this sample video is to show how to do a limiting reactant problem. Now, in this question, it describes the chemical reaction. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. The other products of the reaction are solid copper and water vapor. How many grams of nitrogen are formed when 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide? Also, which reactant is limiting? Now, as with all stoichiometry problems, the very first step is you must provide a balanced chemical equation. So we're going to balance this very quickly. We have nitrogen, hydrogen, copper, and oxygen.
Right, oxygen and everything is found at only twice, so that the order does not really matter. We have 1 nitrogen on the left, 2 on the right, 3 hydrogens on the left, 2 on the right, 1 copper on each side, 1 oxygen on the left, and 1 on the right. So for nitrogens, we need 2 on the left. So we put a 2 in front of the ammonia. That also gives us 6 hydrogens. On the right, we put a 3 in front of the water, which gives us 6 hydrogens, but also 3 oxygens. So we now balance the oxygen by putting a 3 in front of the copper 2 oxide. That also gives us 3 copper. And then finally, we put a 3 in front of the copper on the right, and now it is balanced. Now, for this problem, with all limiting reactant questions, there are 2 starting points and only 1 endpoint. So the easiest way to do a limiting reactant question is to simply do it twice, as 2 separate mass-to-mass stoichiometry problems. And then, whichever one gives us the lower number is the actual correct answer. So for the first one, we're going to be going from 18.1 grams of ammonia, and we're going to the same endpoint, how many grams of nitrogen. When I write out my equalities, first and foremost, I use my mole ratio. Starting point, NH3. So I find NH3, here it is, coefficient's at 2. So I have 2 moles of ammonia. And now the end point is N2, coefficient in front of that is a 1. So I put 1 mole of ammonia. Now I look at the units of my starting point and end point to find what additional equalities are needed. The fact that that is grams means that I need the molar mass of ammonia, NH3. So 1 mole of NH3 is equal to 17.04 grams of NH3. For that, the way I got 17.04 is I have 1 nitrogen at 14.01, and then 3 hydrogens at 1.01. Multiply that by 3, that's 3.03, plus the 14 gives me 17.04 grams. Now I also need, since that is grams there, I need the molar mass of nitrogen. Well, again, each nitrogen is 14.01. 2 of them equals 28.02. And again, it's molar mass, so that's 1 mole of nitrogen equals that. So I set up my grid, 18.1 grams of ammonia. I put grams of ammonia on top. I want grams of ammonia on the bottom, right there. So I have the 17.04 grams of ammonia for every 1 mole of ammonia. Cross that out. Another vertical line. Moles of ammonia on top. I want moles of ammonia down here. Can't use this one, so I use this one. I put 2 moles of ammonia, and it's equal to 1 mole of nitrogen. I cross that one out, and now I have one more vertical line. I have moles of nitrogen here, so I need moles of nitrogen there. I'm going to use these right here, and that's 1 mole of nitrogen is equal to 28.02 grams of nitrogen. I make sure everything cancels out. Grams of ammonia, grams of ammonia, moles of ammonia, moles of ammonia, moles of nitrogen, moles of nitrogen. Leaves me with grams of nitrogen, which is exactly where I want to end up. So, on my handy-dandy calculator, I simply go 18.1 divided by 17.04 divided by 2 times 28.02 equals, and since there are 3 significant figures here, I round this off to 3 significant figures, so 14.88 becomes 14.9. So that's 14.9 grams of nitrogen. Now, I need to do the same thing again, but this time I have a different starting point. I'm going to have 90.4 grams of copper 2 oxide. So I go 90.4 grams of copper 2 oxide. And again, the question is how many grams of ammonia? The mole ratio now is copper 2 oxide, coefficient is a 3. So I have 3 moles of copper 2 oxide, so 3 there, equals, again for nitrogen, coefficient is 1. That's 1 mole of nitrogen. I need, since this is grams here, I need the molar mass of copper oxide. Copper 2 oxide, copper is 63.55. Oxygen is 16. So 63.55 plus 16 equals 79.55. So 1 mole of copper oxide equals 79.55 grams of copper oxide. And for the final equality, I'm going to use the same one here since it's the molar mass. That's grams. I need the molar mass of of nitrogen, which is still 28.02 grams. Now I go ahead and set up my final grid. I put, as always, the starting point in the top left-hand cell. I have grams of copper 2 oxide there, so I need grams of copper oxide there. So I look for it, and it's right there. So I put 79.55 grams copper 2 oxide, and it's equal to 1 mole of copper 2 oxide. Cross that out. I now have moles of copper 2 oxide on top. I want moles of copper 2 oxide on the bottom. I use those right there since only one's not canceled out. So that's 3 moles of copper 2 oxide, and it's equal to 1 mole of a nitrogen. I cross that out. I have one more equality, so one more vertical line. I have moles of nitrogen there. I need moles of nitrogen there. So I take that. I put the 1 mole of nitrogen on the bottom and 28.02 grams of nitrogen on top, since that is what it's equal to. Canceling out, I have grams of copper 2 oxide, grams of copper 2 oxide. Moles of copper 2 oxide, moles of copper 2 oxide. Moles of nitrogen, and I'm left with grams of nitrogen, which again matches the units of my endpoint. So now, again, I use my calculator. I have, starting off, 90.4. So I go 90.4. It's on the bottom, so I say divided by 79.55. That's on the bottom, so divided by 3. That's on the top, so I go times 28.02 equals, and I get, again, 3 significant figures here in the starting point. So I take this and round it off after the 3rd digit, so that's 10.6 grams of nitrogen. Now, in a limiting reactant question, you always choose the smaller of the 2 amounts. What this basically means is that once you get to 10.6 grams of nitrogen, the reaction stops, since you've used up all the 90.4 grams of copper 2 oxide. Even though there's more ammonia, and you theoretically could make as many as 14.6 grams of nitrogen, once you get to 10.6, the reaction stops. So that is how many grams of nitrogen are made. And since the starting point that gave you that amount, the 90.4 grams of copper 2 oxide, that is the limiting reactant. So we would say copper 2 oxide is the limiting reactant. And there are 2 answers. Thank you.